Mario Jara graduated with a bachelor's degree in actuarial science from the Universidad Autónoma de Nuevo León. He holds a master's degree in artificial intelligence from Universidad del Milenio and in astrophysics from UANL. He is a PhD candidate in engineering physics at UANL. His research focuses on developing tools for AI applications in astrophysics, integrating dynamic hypernetworks, quantum classical hybrid algorithms, and Bayesian optimization techniques for hyperparameter training in AI models applied to waveform aberration correction and large-scale data analysis. He contributes to astrophysics community by authoring open source packages, leading workshops on computational methods, and forging partnerships between computational scientists and observational facilities. His work facilitates the adoption of AI-driven approaches across modern astronomy. Mario, can you hear us?
Yes, I can hear you perfectly. Thank you.
Perfect. I hand over the word then to Mario Jara.
Thank you all for being here today. In this presentation, I'll be talking about my project, where I integrate artificial intelligence with the fitting of optical aberrations using a Shack-Hartmann waveform sensor. This work also opens the door to the future implementation of quantum techniques with this type of model. Next, please. As an introduction, let's ask, how do we extract scientific information from an astronomical image? An image like this contains a lot of data about the object's composition, temperature, motion, and distance. It's not just a simple picture as we might think. Behind every astronomical image, there is a large amount of physical information encoded in light itself. That's why ensuring the quality of both the image and the extracted data is essential for an accurate scientific interpretation. Next. When we observe an astronomical object, the light that reaches our optical system is distorted compared to what we expect in an ideal case, that it's a perfect plane wavefront. However, due to atmospheric turbulence, different types of optical aberrations are introduced, such as astigmatism, coma, and spherical aberration. This aberration causes the light rays to fail to converge at a single focal point. So instead, they converge either in front or behind it, which ultimately degrades the quality of the image. Next. In a plane wavefront, what we expect to see in the diffraction pattern is an iris disk, where most of the intensity of the light intensity is concentrated at the center. However, depending on the type and magnitude of the aberration, this diffraction pattern becomes distorted in different ways, as shown in figure number 3. Next. So the complete structure of this project, as we mentioned before when talking about optical aberrations, begins with their measurement using a Shack-Hartmann waveform sensor, and this allows us to quantify the aberrations present in the incoming wavefront. Then we could describe the full processing pipeline, starting with image processing to obtain quantifiable data, followed by the use of Cernic polynomials for waveform fitting. And finally, we can apply artificial intelligence techniques and explore the potential of integrating quantum computing in future implementations. Next. So how does the Shack-Hartmann waveform sensor works? It divides the incoming light into many subapertures using a microlens array. Each microlens focuses the light into small spots, allowing us to precisely measure the displacements of these spots. From these displacements, we can determine the local slopes of the wavefront, providing detailed information about the optical aberrations present in the system. These spot patterns are projected onto observational screen, as figure number 4 shows, allowing us to visualize and analyze the waveform distortions. Next. Once again, in a plane wavefront, we expect an equidistant pattern between all the spot projectants on the observational screen. And however, when the wavefront is aberrated, these spots become displaced from their ideal positions. In other words, instead of a perfectly regular grid, we're gonna observe shifts in the spot locations, and these displacements directly correspond to the wavefront distortions introduced by the optical system. Next. So we're gonna design and implement an image processing algorithm where the main goal is to translate the spot displacements into numerical values that represent each optical aberration. So in figure 7, we can see a real sample where this algorithm was applied. First, the image is converted into cardinal coordinates to identify each spot precisely, and then transform into polar coordinates to better describe the wavefront structures, as we're gonna see in the next slide. Next. So from the measured spot displacements, we can determine the transverse aberration across the pupil. Using the focal length of each microlens, we also estimate the local wavefront direction, which tells us where each light ray should have converged ideally. So by comparing that ideal position with the measured one, we gonna obtain the displacement field then that describe the aberrations. Next. So once we have all the information, we need to express it in terms of optical aberrations, of course. To do that, we're gonna apply Cernic polynomials, which are orthogonal functions that accurately describe optical aberrations. So in this representation, the wavefront phase is expressed as a sum of coefficients, each one showing how much a specific Cernic terms contributes to the total wavefront. So in this project, we use the first 36 Cernic polynomials in Knowles notation to maintain a good balance between computational cost and accuracy. Next. So we work with two matrices. The C matrix contains the derivatives of the Cernic polynomials evaluated at a measured displacements. So it holds all the information about the aberrations, and the Y matrix represents the local slopes of the wavefront, which are related to the transverse aberration, as we saw before. And this forms a linear system where Y equals C is multiplied by the vector of coefficients A, which are the values that we need to determine in this work. Next. So to train an AI model, we first need a sufficient number of samples. We start from the real sample that we saw early and introduce noise into the measurements to simulate realistic experimental conditions that's gonna affect by atmospheric turbulence, which, as we mentioned before, is one of the main sources of optical aberrations. So we reproduce the systems parameters of the San Pedro Martyr Observatory and model it to the zinc effect using a Gaussian distribution of intensity, where the full width at half maximum that is related to the level of atmospheric turbulence, and we vary the same condition from normal to extreme values, generating a total of 3,500 synthetic samples. So we ensure enough data to properly train and evaluate the model in different conditions. So next. And we made sure that the synthetic aberrations follow the same distribution of the real one or the base sample. And here we can see the different magnitudes of aberrations where the synthetic samples show small variations compared to the base one, exactly what we expect when introducing different levels of noise. Next. And we use the least square method as a reference approach to estimate the coefficients A. This method computes the A by multiplying the transverse aberration matrix with the inverse of the C matrix, allowing us to obtain the predicted wavefront W. As shown in the figure, the results demonstrate good accuracy overall. So However, we can also identify areas of improvement, especially in the outliers, since this method cannot fully adapt to all variation in the data or use information from previous samples. So what we can see here is the multiply by this coefficient estimated by the model, multiplied by the C matrix, and we obtain a W matrix. So indirectly, this relationship is related with the coefficient that we estimated. Next. So as a second approach, we use a gradient descent model. So this model defines a loss function that measures the error between predicted and real values. So it is started with random coefficients and ethically adjust them to minimize the error, moving toward the global optimum. So here the learning rate becomes one of the most important hyperparameters and controls how fast the model converge. Next. As a result, this model provides similar prediction to the least square method with higher computational costs. However, it offers an advantage. It's done really on the transparent matrix, which can sometimes lose information due to system issues such as dust or missing data points. Next. As a final approach, we create a dynamic hypernetwork. This model consists of two neuronal networks, one embedded inside the other. So the first network dynamically generates the A coefficients, which are then passed to the main network responsible for solving the system matrix problem. So from this completer structure, we extract the optimal coefficients produced by the dynamic hypernetwork. Next. So this network requires precise hyperparameter selection as it directly determines the model's behavior and performance. So to address this, we apply Bayesian optimization, which efficiently and probabilistically search for the best hyperparameters. And we also use corner plots to visualize these correlations between hyperparameters, helping us to save significant time and computationally cost during this optimization process. Next. So we define a search space for the main hyperparameters and obtain a corner plot showing their relationships. So on the main diagonal, we see the marginal distribution for each hyperparameter, and on the lower panels, their correlations. So this visualization allows us to select the best combination of the model, and the entire process took about 49 hours, which may seem long, but finding these optimal values manually or randomly will be nearly impossible. So, and we wouldn't be certain they were truly the best. So this model allows us to can afford this. Next. Once the model was trained, we applied the same methodology to obtain the optimal coefficient A for the problem, and we observed clear improvements in the central concentration of the data, and even in the outliers, as reflected in the evaluation metrics, we want to see on the next slide. Next. So we observe here that the least squares and gradient descent models show similar performance in all the metrics. However, the dynamic hypernetwork achieved a slight increase of about 1.4 in R squared and a significant improvement in the MAE and MSE, which are lower by an order of magnitude. So this means the model produces small errors, and considering the RMS of A is higher, it suggests that the previous methods likely underestimated the total aberrations, with the dynamic hypernetwork captured them more accurately, and also it reflected in the residual plots. Next. So an additional advantage is that when we analyze the outliers, we can see that the dynamic hypernetwork performs better even in regions where limited information. So this is one of its main strengths. It can adapt efficiently even when the available data isn't enough. Next. So The quantitative metrics remain consistent when we evaluate and test the model using 500 synthetic sample instead of just one. And this dynamic hypernetwork continues to perform better, faster, and more accurately across different aberration magnitudes and sample tests. Next. So, although the dynamic hypernetwork achieves great accuracy and speed, its performance still depends on hyperparameter tuning. So, traditional methods like Bayesian optimization or random search can take hours or even days to explore the full search space. So, a promising alternative is quantum Bayesian optimization, which can evaluate many configurations simultaneously, reducing time and improvement converge. So other quantum approaches such as Gaussian process and quantum Monte Carlo can also accelerate covariance calculation and expectation evaluation, and thanks to amplitude estimation, achieving a quadratic speedup. So in the future, combining quantum optimization with dynamic hypernetworks could lead to a new generation of adaptive and faster models for optical systems. Next. So, in conclusions, artificial intelligence models prove to be an excellent alternative for optical aberration fitting, offering precision, adaptability, speed, and scalability. So these dynamic hyper networks show strong potential for real-time applications, such as adaptive optics, where these capabilities are essential. So moreover, this methodology could transfer to other domains that require flexible adaptation to different number of inputs. So, and finally, quantum computing represent a promising opportunity to accelerate hyperparameter optimization and enhance global converge in complex models. Next. So for this work, I use key references. The book by Hedge provide theoretical fundamentals about optics, reference about Shack-Hartmann waveform sensors, other references like Cernic polynomials in nose notation, and finally about Bayesian optimization. Next. So these results are also summarized in a research paper published in the Optical Engineering Journal. And I would like to acknowledge my advisor, Dr. Carlos Guerrero, and collaborator, Dr. Juan Tapia, Dr. Joel Herrera. Thank you very much for this presentation.